Aduh. Oh, it works. Testy. Testing. Fair enough. Fair enough. All right. That can go. Oh, that can go. That can go. This can come. Ba, 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 ba. And shall we get some music? Let's get some lo-fi girl. Lo-fi girl. Shh. Radio check. Let's see how that volume is. Yep. Turn it down a little bit more. Ready check, ready check. With music radio. 1, 2. Oh, it's muted. Ow. That's loud. One, two, one, two, one, two. Check. 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 Alright, that's good enough. Whatever. That's insanely loud. Okay. All right. Where did I stop? Implement STD variant. It's a 2D vector. Before we even do anything, let me get variant done. So in selection results, well, let me read on it real quick. Different types. Blah 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 blah. Okay, so STD, there are all possible types it might store. So we have to import anything? Variant in utility. Include variant. I already have string utility. All right, selection result using result type. Let's see. Variant. What is the using keyword? Oh, it's like using namespace standard. I'm using. It's in base F. Namespaces, inheritance. Allow specify in particular namespaces. So you want to avoid typing out. Okay. Using namespace standard, so you don't have to put std in front of everything. Using for inheritance. Not necessary right now. Aliasing, not necessary right now. Okay, oh, that was long enough. Okay. Directives. Okay. Very well. So variant type, all possible types, and then the variable name. So using result type as a variant. What? So here, before we even do that, why can't I import it? It's good for now. I am on. I just got to the matrices chapter in on Khan Academy. This guy. Not that far in though, but right here. That's where we stopped. I was watching a video on it the other day. It's not complicated, so should be able to breeze through this and get down here. Yeah. Yep. Trying to think of what I'm trying to do here. For some reason, I can't import variant. STD variant. What? Variant. What do you mean? Include variant. Include utility. Oh, I included it twice. Is that why? No, I don't think so. Static. STD variant. Hello? Did they remove it from C++? Question mark. Not using variant. Variant int double standard namespace. What is the problem? Variance, 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 variance. Maybe it has to be, it's a R value. Maybe that's why. It has to be on the right side. So if I do using result type std, nope. I don't get it. What? Okay, here, hold on. Close and open. What is going on? Was it removed on C20? Because that's what I'm on, I think. Is that what it is? General. I'm on C14. That's why. I'm like, what? I should be on 20. Okay. And that's on release. What's on debug? It's on 14 as well. That's interesting. Okay. Hope no other part of my code breaks because of that. Let's make sure it works before we even try to. Now that we switch versions. Make sure we can still plot. 8. So plot the vector 1, 2, 2, 4. And then I don't see 1, 2. Oh wait, it's the same. It's the same line. Let's try a different vector. Let's just do 1, 0 and 0, 1. All right, there you go. All right. So it still works. So now we should be able to. So using results type equal to std variant. There it is. Std mono type monostate. My bad. Monostate. and all the types we can possibly want. So double vector 2D and vector 3D. So we don't have to essentially do this. So monostate vector 2D, vector 2D, vector 3D. Okay. And that's our result type. But it can just be a good old double or scalar, essentially, as well. So we want to add double. Okay. I'm not exactly sure what monostate does. It's commonly used as first type empty. Okay, uninitialized. Okay. That's just not initialized into anything, I guess. Alright. And then we can, instead of, we can delete these and actually just make a result type. Result type resultant. Just one resultant. That way, we don't need 1, 2, or 3. We don't need any of these lines. We can just pass. We can just pass. Where is it? So instead of returning a resultant, for example, in case 7, we're returning a scalar. We don't need to set this flag to true. We can just pass resultant. We're just passing a scalar, and it's automatically gonna figure out what value it is. In theory, I think that's how it works. I don't know. So we just set, where is it? Set resultant is equal to that. We don't need that part. Resultant is equal to that. What do you mean selection result resultant? Did I declare a different variable up here? Yeah, I did. All right. Well, no, that's fine. Resultant. So resultant dot resultant rather, not dot resultant scalar. Dot resultant is equal to that. And we don't even need an if-else statement. We can just do resultant dot resultant since it's already gonna check if it's a 2D or 3D vector, essentially. So first we just go ahead and delete these. Don't need those, and we shouldn't need this either. Actually, before I do any of this, let me commit this to GitHub real quick in case I gotta go back. Commit, commit. Hold on, I gotta make sure the origin link is right. Yeah. All right, commit. I'm gonna create a new branch. Git new branch. Do I? Wait, this was a stable version, so I just go ahead and actually delete this. Delete these, rather. Did I change anything down here? Yep. Not resultant. I forgot what I did here. Let's just Control Z all the way back. Here it is. Result type. Yep, alright. I don't want to type this again. Let's go ahead and do this. Copy that. Delete. And this is essentially the regular version. Can delete variant. And commit. What did I implement? I implemented plotting. Plotting 2D vectors with the gnuplot. Removed MATLAB support, and then all right, that's fine. Need that main 3, 4, 5. Just can't get deleted. I don't need that. Main CPP. All right, commit staged, and then go ahead and push it. Make sure that's good before we github.com, Visual Studio, and just pushed right now. And a CPP. Cool. That looks good to me. All right, I should have deleted that as well. All right, so now we can actually start. All right, so include variants and put our line back. Double. Oh shit. And we don't need a vector 3D and a 2D. And we don't need a resultant scalar. We just need a results type. Result type resultant. Result type resultant. And then we can come down to all our cases and case 7. ¿Qué pasó? Why you staring at me? Huh? Yeah, bro. Why you staring at me? Why you staring at me? Your TV is up there, or your laptop. You're staring down. Speak your mind. Yeah, you're staring over here. I can see where your eyes are going. I'm kidding. No, I wasn't. All right. Whatever. Whatever. If you can delete this if statement. Wait, no, we still need to check if it's a 3D vector or a 2D vector. Well, then I just need to implement that for vector input as well, right? It can either be a 3D vector or a 2D vector. Shit. All right, we're gonna need to implement that for this as well. So, the result type can't be a double. It can be a 3 or 2D vector. And then results type. Outside vector. Vector. Okay. 56 errors. It's gonna be a long ass. Oh, Jesus. Okay, so now we need to go to everywhere. There's a vector 3D underscore. Let's expand our whole code. This is the worst part right here, man. Every single place where we have vector 3D or 2D, we need to change that to vector. Essentially rewriting the whole code. Bruh. No way. Damn, bro. Alright. First things first. Control F. Everywhere we have vector 2D underscore. Show me all of them. It's a passed in vector. Vector input. Vector creates a vector. And it goes to set vector. So vector dot is 3D. If it's a 3D vector, I just want to set it to vector dot. I just want to set it to vector dot vector dot x. What? Vector dot vector. Vector if it's type 2D. Okay, we're cooked. Huh. Huh. Here, I'm not gonna mess with this right now. And try to implement a, I'm gonna leave vector input alone for now. And just work on resultant. Resultant. This returns a scalar. So dot resultant. That's fine if it's a 3D vector. Else, if it's a 2D vector, dot resultant also. And then return. We don't need this. We don't need to check if it's scalar anymore, because it will just tell us. So we can do away with those flags, I believe. We can do away with is scalar and is 3D, because we don't need to check that anymore. I'm gonna do away with this for now as well. All right. So we don't need that. And true vector have the same dimensions. If it's 3D, set the resultant. If it's 2D, set the resultant. That works. Okay. And here, we'll come back to that. Let's do 6. Again, just returning resultant as well in the else statement. Resultant. Don't need to set the flag anymore since it automatically does it. And then case 5, we don't need to check if it's a. Set the resultant to a 3D vector. We just need to set it to resultant. And we don't need to set the flag as well anymore. If it's not a 3D, print out the error. We could really just set the error flag. Because if it got this far, that means it was the same dimension. But, so instead of this, let's, we'll come back to that. Set error flag. Oh, what's up, man? What's up, Armin? Oh, my bad. Welcome, welcome. I'm gonna hang up if you keep looking at me like that. You're late for class. I don't know if you left. Well, welcome to the stream. I'm locked in. I'm not looking at chat. Set error flag. Let's come back and set error flag. All right, and the resultant's fine. And now the dot product resultant as well. And then else, it's a 2D vector, then we return resultant. Don't need to check if it's scalar. All right. And then I should have done this one at a time, because if something goes wrong, I'm gonna spend like 2 hours debugging, trying to find it, because I'm changing 7 statements at once. Resultant that resultant first vector, vector 3, scalar. That's fine. So it returns a boolean double value. So this text returns a double. All right, cool. Else, it's a 2D vector. Return a 2D vector. Regardless, it's gonna return a double. All right, that works. Leave these open. Case 2, return. Don't need the flag anymore. And we need to return just resultant.resultant. And resultant.resultant. Okay, and then case 1, don't need the flag. Resultant.resultant. And resultant.resultant. Okay. And then we need to, at the end, return just the whole resultant. And after we run perform selection, we go to process result. Yep. All right. There's an error flag. This is not implemented yet. There's an error flag. So if result, this is where we need the in place, I believe. So what is in place? Not in place, holds alternative. So check if the given type of data is stored inside the variant at the given moment. Is there an example? So 42 if, okay. So if holds alternative int my variant. Okay. So if there's an int in my variant at this moment, then you want to print the int. Then you set my variant to a double and print the double. Okay. So if results, if rather holds alternative, std holds alternative, if it's a double, then I want to, what is the syntax? Double bracket, result, I believe, right? Is that what we pass? Result, yeah, results. Oh, result is a selection result. So result dot resultant. Yeah. So if result dot resultant is a double, we know we have a scalar. We know we have a scalar value. So we want to print resultant scalar is result dot resultant. Why is that throwing an error? Result dot result. How do you print from a you can use get. So get double my variant. So get whatever my variant. All right, so get. So instead of this, it'd be get double get double result. Result dot resultant. Maybe. Yeah. Huh? Sure. What are you looking at there, bro? Is it a baby? What? Let me see. What is this? Are those supposed to be abs? Are those supposed to be? I'm just kidding. Good job, there, bro. Good job, there, bro. Good job. I think that works. So now if results dot, we don't need to check that. So if std holds alternative, here, do this. If std holds alternative, vector 3D, vector 3D. So it's a 3D vector. Result dot resultant. stdc out. stdc out results. So we need to get again. Rather just get the get vector 3D. Vector 3D results dot resultant. And then on the result dot resultant, we need to get the x value. I think that's correct. Then we need to do this over here, but for the y value. For the y value. And then on here again for the z value. And I should handle that. Else, if it's a 2D vector, we do get vector 2D vector 2D results dot resultant dot x, and then we want to do the same thing over here for the y value. That one. I think that works. I think that works. I think it works. For now. Alright. 0 errors. There you go. It's just warnings, nothing important. What is this? Oh, it's supposed to return something. Oh, we're never gonna get that far, so if we do get that far, I guess just return false. Because if there is an error, that means that didn't work. So return false. That should take care of that, I believe. No? Or are you talking about the function in there? 142. I don't know, bro. You don't need to return anything. Yeah. If it ain't broke, don't fix it. All right. I think that should hold for now, so let's just test. So vector addition. If we want to add 1, 2 to 1, 2, we should get the vector 2, 4, and that works. Vector subtraction, subtract 10, 10 from 5, 5. We should get 5, 5. Okay. Vector multiplication, multiply 1, 2. All right. Multiply 1, 2 times 3, so that should be 3, 6. Should be our new vector, and it is. For dot product, take the dot of 1, 2. Actually, if you take the dot of 0, 1 and 1, 0, you just get the inverse, right? So let's just do that. 1, 0. Oh no, you get 0. Never mind. I was thinking something else. Dot product returns a scalar, not a vector. Alright, cross product is a 3D vector only. So take the cross product of 1, 2, 3, 3, 2, 1. I'm guessing that's correct. I'm not gonna check because it was correct last time. I didn't change any code. I just changed the way it was done, essentially. Now let's see if my plot still works. So I can do 1, 2, plot the vector 1, 2 with 8, 8, 8, -9. And it does. Okay, so if you take this vector and you put it there, the resultant vector should be that. It's just normalized, that's why it looked weird. All right. Very well. Go and exit. Yeah, I think that handles the return value. So now we can work on actually plotting 3-dimensional vectors. I already implemented plotting 2-dimensional vectors. So there's that. That's this. But we need to do it on 3 dimensions. So from here, we're actually getting that value from case 8. So if it's not a 3D vector, we do that. Else, I mean, it's a 3D vector because it's a true or false. So else, we want to plot a 3-dimensional vector in here somehow, and its resultant vector as well. I'm gonna come back to the resultant vector. For now, let's just try to plot the vector. I'm not exactly sure how plotting 3 dimensions in gnuplot works though, so let me see. Let's watch a video real quick, I guess. See if you find something on YouTube. I remember I saved 2 videos on this. If I remember. Where is it? Was it liked videos? No. No. Where do I see my, not playlist? Yeah, sure, playlist. All right. Things I will forget. And actually, I don't remember where I saw it. 3D vectors. gnuplot. I'm pretty sure you just need. So instead of it taking XYZ, XYZ, it should take 3 values. So I think this was the one I watched.
Study.com gave me what I needed to pass both tests on the first try. And here's the proof. I'm shooting this video from my classroom.
Here's just a very quick tutorial about using gnuplot to plot more than one vector valued function at a time. If you parametric surfaces, press set. We're just going to dive into the command.
What does parametric mean?
So basically, I type in set parametric, press enter. And you'll see it says dummy variable is T for curves, U or V for surfaces. Since we're going to be doing 3-dimensional plots, we're going to be using U, not V just yet. We're just going to be using U. Don't use T. So what do? We just type SPLOT, that's for 3-dimensional plots, and say we want to plot cosine U, sine U, and U. We press enter, and then we get that plot. I'm just going to move this into our field of vision so we can see it.
So if you want to plot 2 things at once, you just use 2 S plots, I'm guessing.
And sine U.
Yeah, okay. So you just, all right. Oh wait, no, he put it in one statement though. S plot cosine U, sine U, U. What is the layout? Is this the X1, X1, Y1, Z1? Or X1, Y1, Z1? And then X2, Y2, Z2? Or is it X1, X2, Y1, Y2, Z1, Z2? I wish I could find some documentation. That'd be nice. It's almost like those exist. gnuplot 3D vector documentation. I'm not plotting from a file. Where's the documentation? Let's plot. Just plotting points is what I'm curious about. How do you plot points? I don't want to plot a sine wave, which is what everyone seems to be doing. Here, this is gonna be like one of those things where we just have to test, I guess. So let's just do the first vector dot vector 3D. Oh, first we're gonna normalize all of them, just like we did up here. The first vector dot vector 3D dot normalize. And take our second vector and normalize it as well. Second vector. Second vector. Cool. And then we're gonna need a tuple. I know that. But how to use a tuple? Because this is a vector of one tuple. And if I recall, plotting in 3D, you need. Well, this guy's video was the most helpful, honestly. So you fed splot, assign 3 values pretty much: cosine, sine, and u. X, Y, and Z. I'm guessing, maybe. I don't know. Let's find out. So if we feed splot, the X is always going to be 0, 0 in my case. The Y is going to be, the Y and Z is what's going to be different. That's not true. I don't know. Vector 1. Here. Just give me that. Paste that here. And I need a \n here. Just for now. Do that. It's gonna be splot. And then gp.send. Vector 1. This is probably gonna throw an error when we go to plot a 3D vector. So plot vectors, let's plot 1, 2, 3, 2, 3, 1. Yeah. The Z values are undefined. I mean, this is the same thing as up here, so this is a 2-dimensional vector. So maybe that's the X. And that's the, wait, this is the X. X. Alright. So instead of 4 doubles, let's do 6. Double, see if this works. Double, 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 double. And then in the tuple. So let's do 0, 0, 0. And then first vector y. And then first vector dot vector 2 3D dot c. And it should be vector 3D as well, and vector 3D. Maybe? Question mark. Maybe it works. Maybe it doesn't. All right, plot 2 vectors. 2, 3, 2, 3, 7. 1, 2, 12, 12, 12. Huh. It worked. Okay, but is this the correct vector? That's the real question. So it looks like the point is, it's not telling me the point. That's super crunchy, dude. Hold on. I wish I could know what this point is. That'd be nice. Because on the 2D one, you can just like scroll and see what the point is. What point is that? That's what I want to know. Looks like that is 0.9, right? No, like 0.7. I could just open a file and read what vector it's plotting. Never mind. It's not updated because we're no longer writing to the file. God dang it. All right, I deleted that. I don't know if this is correct. So here, let's just plot something simple. Let's just plot like a 3D vector, but the vector is 0, 0, 0, essentially. And that should just, well, 1, 1, 1. Oh, no, 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 no. If we do 0, 0, 1, 0, 0, 1, that should just be the z-axis. The x and y should be flat, I think. I'll just do 0, 0, 0 here. That's fine. Yep, so just go straight up from the z-axis, which is correct. So that tells me it's plotting that correctly. So if we do, let's plot 1, 0, 0. That should just be the x-axis. And 0, 0, 0 on that. Doesn't matter for now. And that should just be the x-axis. Yep. Okay. This is so weird. And then if we do, y should be 0 as well. So if we look at y, we can get a good look. Y is 0. X is 1. And then z should as well be 0. Right? Yep. All right. And if we plot just on the, if we plot just on the y-axis, it should be 0, 1, 0. I'll just make this 0, 0, 0 for now because it doesn't matter. Just on the y-axis, as you can see, we are sitting at 1y, 0x, and 0z. Cool. So it works. All right. Fair enough. Let's go ahead and implement the remaining, the second vector rather. So it's the same thing here. Just duplicate that. Vector 2. It's going to be second vector, and our second vector, XYZ. S plot. We need to call this again for vector 2. Just this really. So we'll just take this. And the only thing we need to change in it is the S plot. Also, we need to create a Z range as well, since we don't have one. Control D, since we're not dealing in 3D. But I'm curious, will that create a Z range on a 2D vector plot? Because I don't want a Z range on a 2D vector plot. I might have to put it in the if statement. So if I just do 1, 2, just 0, 1, 1, 0. Does that create a Z range? It doesn't. All right, we're good. Cool. Cool, 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 cool. All right. Vector 1, vector 2, and then we need our resultant vector in here as well. So create a resultant vector, which is going to be vector 3D resultant vec. And it's going to be our first vector. First vector, vector 3D plus our second vector, vector 3D. Put that in parentheses. And You just dot normalize it at the end. I think that should yield the same result instead of doing it on 2 lines like this. Yeah. I guess declare this at the end. Doesn't matter because we already got it. All right, that works. And then we need a third one of these in that case to plot our resultant vector. So resultant vec dot x value and resultant vec dot resultant vec dot the y value here, and then resultant vec dot c here. In fact, let's see. Okay, so that should plot our resultant vector in here. And now we need to send all 3 of them. So we need to send vector 1, vector 2, and vector 3 to gnuplot. I called it vector 3, right? Yeah. All right. That's a 3D vector plotted, I believe. Let's try it. Looks fine to me. Looks fine to me. So if we want to plot the 3D vector 0, we'll plot the vector 1, 0, 0, and 1, and 0, 1, 0. It doesn't have any z component to it, so this is really a 2D vector on a 3D plane. Yeah, as you can see, it has no z component to it. But that's the resultant vector. A y is 1 on the purple one. So that's a first vector. Our first vector should be x rather. So as green saying, I probably messed it up somewhere. I need it to match the entry. So 1, the first vector should be here. Let me make sure. Gotta find where I messed the entry up. Because our first vector should be, if I plot a 2D vector, 1, 0, and 0, 1. Our first vector should be the x-axis. It is the x-axis in this case. So why is it wrong on a 3D one? Purple vector 1. Did I mess it up? One zero zero 0 1 0. X is this way. So vector 1 is x. Okay, never mind. I'm tripping. And this is y. Yeah, it just looks weird. So it's correct. It is correct. Alright, and we can add a boundary somehow. I know it was on this video. Set label z. Set z label. Essentially this right here. Set z label. Z-axis. Font. How about to get 12? That's fine. And then double this. Z-ticks. 0.1 as well. Z range. Cool.
Pretty much what everything XP, and you can change that around.
What's the command for the
And there you can
border?
see it. Sign, don't use T. V, that's for 3D. Sign U. I'll make it a little bit grid. If I press it again, the grid disappears. If I press the B button, that provides a bounding box. And if I press...
What's the command for the bounding box? It's parametric. Changes the meaning of plot. What? What do you mean changes the meaning? And you have a message, dummy variables is T for curves, UV. That's if I want to mix it. Here, let's do this. Set parametric. See what that does. I didn't do anything. I'm confused. Huh? Can you come say hi on my stream? Say hi in my stream. I'm bored. It's just me in here. Huh? On YouTube. Mm-hmm. What? I'm lonely. I got no viewers. All right. I am on both at the same time. Yeah. It's pretty cool. I don't. Zero. He's gone. This is like minutes ago. I don't care, Deborah. There's no one in here. All right, set vector. What? Okay. Huh? I still don't know what set parametric does. I like to plot a function. See how to do it. Fuck no. No, I won't. Go ahead. It's not like this is saved at all. Okay. Okay, Deborah. Please check how parametric special files have sampling. Boom. Set multiplot. Parametric curve. I don't think I need parametrics. I don't even know what it does. So here. How do you put the bounding box? Bounding box. gnuplot box. gnuplot set box. Is it border or box? Set box. Error. I don't know why the website's not working. Set box with value. Relative, I guess. Set box with 0.5. There you go. So duplicate. Maybe. You're on the phone with me, Deborah. I just told you to watch. I'm sorry. Because I was bored. Hey, how are you doing, Deborah? How are you? Excuse me? Excuse me? I'm just talking to you. You'll be okay, I promise. The world is gonna go around, okay? And you'll be fine. At the end of the day, you'll be fine. You're gonna go to bed, you're gonna wake up, and you're gonna realize it's the exact same. Okay. One, one. Negative one, negative one, negative one. You'll be fine. There is no boundary. What the heck? Mm, 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 mm. I have to say with boxes. Oh, okay. Where are we? With boxes at the end of the plot. With boxes. Maybe. I feel like that's in the wrong place. Yep. Duplicated. What? And plot options. What do you mean, partner? Why doesn't their website work? Docs. Where's the documentation?
So let us, right. So I want to plot here of the function that we have taken, sine x into cos y. Okay. Now, some kind of warning move was quite important. This three-dimensional plot. You have to write. We use it might change well. Okay. The next function that we have done to remove the hidden lines, we have used hidden 3D to make okay. X. This command. The next part is to replot out earlier. It was quite set. Okay. Now, if you want to change the color, don't so you and
What I'm looking for. That's fine. I guess we'll do without the boxes. Whatever. Forget about it for now. So 0.5. Too many ticks. Too many ticks going on. Yummy, yummy. That's better. All right. Yummy, 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 yummy. No. Not at all. Shh. Oh, you gotta go to work tomorrow. It's bedtime. Glad the lights are off. Bedtime. You gotta go to work tomorrow. Implement standard variant selection result struct and then plot in here. Okay. And result in that is plot is true. So let me just return resultant and check if is plot. If results that is plot. And then I want to just call plot in there. Plot vectors. First and second. How would that work though? So I need to actually return a pair of so an STD variant, I need to add a pair. It's gonna be a pair of STD pair. It's either gonna be pair of double or a pair of 3D vectors. So I guess we could just comma STD pair vector 2D vector 2D or vector 3D vector 3D, or STD pair oh, it's not working. So we get a pair of 2D vectors or a pair of 3D vectors. And so when we do that, we can come down to plot two vectors and then set as plot is true, and then essentially resultant dot resultant's equal to a first vector, second vector. All right. No. Is it not working? Do I not remember how to use std pair? Read to vector returns a pair. We use tie to read the pair. What? Where's the read vectors? Read to vectors. It just returns a pair of vectors. v1, v2. In this case, I'm returning a pair of vectors. First vector dot all right, I see the problem. So I need to check if it's two-dimensional or three-dimensional vector. What is a resultant? Return. It's a result type of this. But it has to be one of these. So I can just return, instead of expecting a pair of a 2D vector and a 3D vector, I should expect a pair of vector input. Vector input, vector input. And then I'd still need, no. So I just put an if statement, check. So if it's a, I'm not gonna plot vectors here, so I'm just gonna do if, I took away the is 3D function, so that's not even gonna work. std, what's the name of that function again? std variant, std variant, std variant. If holds alternative. Holds alternative if it's a 2D vector. To 3D. If it's a 3D vector, then first vector. First vector dot what? I guess I just check if it's 3D, like a regular version. Good night, Deborah. Sleep tight. Don't let the bed bugs bite. Okay. The first vector, that is 3D, right? If it's a 3D vector, then I just need to set resultant that Vector 3D. Dot vector 3D. So now that should work. Maybe. Huh. Isn't this a pair? Do I not know how to use pair? What's the problem? Make pair. I have to lose my mind. I guess I don't even need that. Now it works. Like, how does that make sense? I don't need to plot vectors here. And we don't need his plot either. All right. When we break and return to process result, if let's see, holds alternative, holds a pair, right? So vector 2D. Can I just say hold alternative FCD pair? Shit. I don't even know what I just did here. If hold alternative. std pair vector 2d. Yeah. Maybe. It's not working. Old alternative. Matches. Vector 2D result. I guess we can just use the is plot flag. I kind of wanted to delete that. Can you help? Sick, bruh. I said, can you help? What do you think I said? Okay. Okay. Nothing, it's fine. You, it's live. I'm not bending. Sorry. Just go to sleep. Don't worry. I'll figure it out. Thank you. Old alternative. Pair. 2D. If that's what it is. Resultant. Okay. I'm like, what? Close up all these spaces. It's hurting my eyes. So if old alternative needs to be an or statement, really. Or the same exact thing, but vector 3D. Goes to that vector 3D. Then I want to simply print I want to call, where is it? I deleted it. I want to call plot vectors, first vector, second vector. So plot vectors, results dot resultant dot, no, what is it, get? Nope. Get double, in this case it'd be a std pair, CD pair. Vector 2D. And CD pair. Vector. I'm curious what the error is going to be if I pass in a 3D vector and it's expecting a 2D vector. Uh-oh. So I just try catch. If it's one of these, alright, here's what we're gonna do. And break these up. Multiple else ifs. It's just confusing, I know. Delete the or statement and give me that. So if there's no error flag, if it's a 2D vector, we want plot vectors, plot vectors, plot vectors, get, std get, get. I don't think that's a thing, no? It's just get, right? Std get, get std pair vector 2D 2D. I don't think this has an SC in front of it. What? So get the pair of 2D vectors and then plot the resultant dot and plot the resultant dot x, the first rather, and then do this again. Here, let's just make this easy on the eyes. 2D v1 is equal to this. The 2D v2 equal to second. And now we want to plot v1, v2. It's supposed to be a vector input. Oh shit. Vector. That's a 2D vector, not a vector input. This takes a vector input. Wow. Well, there's that. Um, so it should just make pair of vector 3D, and this should just essentially take vector input, I believe. Take vector input, vector input, no vector input, vector input. Okay, but now we gotta change our. God damn it, bro. What? Nah, hold on. The 2D and a 3D vector. Why is my plot vector function taking vector input? It should just take a. Cause I don't know if it's a 2D or 3D vector. Go to sleep. Put the phone down. It's bedtime. It's bedtime. Hello? Bedtime. Bedtime. Yummy yum. Bedtime. Bedtime. What's up, Mr. Mouse? I hope you're not in here. Yeah, what's up? They're on your ass. Said they're on your ass. I said they're on your ass. I'm complaining. What's going on, Miles? Mm-mm. I went for a run yesterday. That hurt. I went for a run yesterday. It was good. Mm-mm. Yeah. What? You saw my watch. No. Vector input. I went once yesterday. There's gonna be no difference. The Stairmaster is harder. Mm. Yeah. Whatever. Vector input, vector input. I need this to just be a 2D vector or a 3D vector. But I can't do that because then I won't know if it's 2D or 3D that I need to plot. So I need to. This takes vector input. Shit. No. small mistake is gonna make me change the whole thing. That's crazy. All right, well, it's just taking vector input, vector input, vector input, vector input, and a bunch of errors. All right, first one, selection resultant. What's the problem here? Cannot be referenced. Resultant cannot be referenced. What? Selection result. Resultant. Just that. Cannot be referenced. Why? Because nothing was set to it. Resultant, so instead of result dot resultant, this needs to be resultant dot resultant dot what? Result type. And it's going to be one of these. That is correct. Resultant dot double, for example. Do I have too much stuff in the variant? Is that what it is? I don't get why this changes it. It's the same thing. I just simply storing vector input in this now instead of vector 2D or 3D. Oh, this is double. I don't need two of them if that's the case. Yeah. Does that fix it? No. Result that resultant. Yeah, it did. Okay. I had two of the same thing. You know? Result dot resultant. So now it's just equal to that. It's gonna set it. And this, in this case, this would be a 3D vector. It's gonna equal. Yeah. The first vector is a vector input dot vector 3D. In this case, it'll equal a 2D vector. Okay. And that works all the way until we get to plot, I believe. So yeah, we don't want to pass in a 3 or 2D vector. We just want to pass the whole vector in, since it's a vector input. We don't need to do that twice. And we don't need isPlot. So we don't even need to check if it's 3D. We can just pass it in, I believe. So we don't need to set isPlot because we don't need that. Okay. So that should now let me, I believe, plot get we get a pair of, this is wrong. If it holds alternative vector input, vector input, vector input, vector input, result dot resultant, then I need to get the pair of vector input and then just send it to vector input, not dot first. Why is this not working? Oh, vector 2D dot. So this should be vector input v1. What? Oh, dot first, indeed. Yes, so we want to get the first vector input. And we do the same thing here. This is v2. Delete that. In this case, we're getting the second and the pair. And then we're sending it to plot vectors, so we don't need that. We don't even need to check if it's 3D. Right? Yeah. This should work, maybe. And we plot vectors, so we come up here with 2 vector inputs. And then it checks if the first vector is 3D. And let's run it, see any errors. Yikes. Alright, 7 of them, nice. Vector input undeclared identifier. I need to declare vector input before selection. Bruh. Okay, it worked. Alright, let's plot 2 vectors. So 1, 3, 3, and then 2, 1, 1, for example. And then it works. Yeah. Alright. Plot 2 vectors. 1, 0, 0. And 0, 0, 1. That's X and Z coordinates. And the resultant is just a Z coordinate for some reason. Oh, the resultant is in the middle. Never mind. And that's the X. Right. Yeah. Alright. And for plot a two-dimensional vector 1, 0, 0, 1, X and Y. Cool. I think everything still works. 231 plus 333. So it should be 564. Yeah. All right. So looks good to me for now. Till I figure out something is broken tomorrow. Till I figure out something is broken tomorrow. This looks fine for today. Like this. Bring up this guy. Bring up this guy and get him to comment my code. How do you start a new chat? There you go. Comment my code for me. Do not change a single line of code while we add comments. Maximum clarity and future maintainability. All right. Oh, of course it froze. I need to buy the pro version. I'm broke. No. All right, whatever. I'm not gonna comment it today. I'll do it tomorrow. Before we go though, we need to push this to GitHub. I think it's pretty stable. So let's open a terminal. Git status on master branch. Cool. Git add -u class. I'm a rookie using Git. I don't know what I'm doing on here. So Git log. That's the last commit we had. So Git commit -m with the message added 3D plotting, and then plus refactor factoring. That should be fine. That's pretty much all I did, right? 3D plotting, and then we cleaned up the code. Yeah, I think that's all I did. All right. So that's good. Where's the refactor? I'm trying to think of if I did anything else. I don't think I did anything else. Refactoring. No. I mean, the commit will show it, I guess. If someone's curious. I don't think anyone's curious. Replay is refactoring. Git commit. Git log, rather. Alright, it's in there. And then we can go ahead and push it. Git push Origin, master. GitHub. Has it pushed it? Yep. And it's right there. Added 3D plotting plus refactoring. You see our changes. We changed selection results. Cleaned it up. Yep. All right. Cool. Need to delete this document. Whichever one is the MATLAB. This guy. May not CVB. Looks like it's all in there. All right. Cool. That finishes that for today. That finishes that. All right, yeah. Linear algebra and then bed. The game is over. Who won?
Broiling hot outside. Phenomenal atmosphere inside here in Houston for the latest installment of a rivalry.
Who won U.S. versus Mexico?
100 years. It's the CONCACAF Gold Cup
For real?
final.
Damn, they came to Houston and beat them. Ay. What was the score? 1-2. They came in their house and beat them. That's crazy. They did that for all the ice people.
Back inside, it was behind Freeman. It might find him a second time. US have numbers and what a big tackle by
They did that. Good job, Mexico. I'm just kidding. Oh, all right. I'm tired. I don't even want to. Fairy. I already know this, I think. So let me, while we watch this video. Ow. Ow. Why are you still up, Deborah? It is. What time is it? 9:04. 9:04. Huh? It's 9:04. I'll be right back. Oh. 9:04. Let's see.
One, 3, and 4.
I think I know how to do this. I don't even need to watch it because I know how to do it. Maybe. Gotta make these two zeros. Just to be row 2 minus row 1 minus row 2. 1, 1, 1, 3. Row 1, so 1 minus 1 would be 0. 1 minus 2, -1, right? And 1 minus 3, -2. And 3 minus 0 will be 0. 3 minus 0 is 3. Cool. Let me just write 1, 3, 4, -2. Now I'm gonna make the 1 at the bottom 0, so row 1 minus row 3. Huh? That's not the first time. And keep row 2 the same. And then 1 minus 1, 0. 1 minus 3, 2. 1 minus 4, -3. And 3 minus 2 will be 3 plus 2. So that's 6, 5. Alright. And then need to get this -2 to a 0. So you're gonna do 2 times row 1. 2 times row 1 plus 2 times row 1 plus row 3. This will be 1, 1, 1, 3, 0, -1, -2, 3. 2 times row 1. Two times 1 will be 2. No, that won't work. We do 2 times row 3. Oh, no, row 3 minus row 3 plus 2 times row 1. So row 3 would be, in this case, would be 0 plus 2 times 1 is 2. 0 plus 2. So I'll make that 2. That makes no sense. Huh? Oops. Maybe I do need to watch the video. Two times row 3. What if I flip it? So make that my pivot. Then 3 times what? Yeah, if I flip it and make that my pivot. So 1, 3, 4, -2. I'm trying to get that to a 0. Then I do 2 times row 1 minus row 3 is going to be 1 minus 1 will be 0. Row 1, 3 minus 1 will be 2. Now we just get the same thing because we gotta do 2 times root 3. 2 times root 3. Bruh.
And let me show that it's augmented. And then they equal 3, 0, 3, 0, and 1 minus 2. Actually, a better thing to do, because I eventually want this to be a 1 anyway. Let me replace this row with the second row minus the first row, instead of the first row minus the second row. I can do it either way.
Second row minus the first row. Isn't that what I did? So 2 minus 1. Nope. 2 minus 1. That gives you just 1. 1 minus 1 would be 0. And then 2 minus 1. So it would be 2, 1, and then 3 minus 1 would be 2. 0 minus 3 would be negative 3. And then for the third row, minus 1 would be 0. Three minus 1 would be 2. 4 minus 1 would be 3. Negative 2 minus 3. Okay, so I want the 2 gone. So 2 times row 1. That makes no sense because it gives me a 0
So
back here.
the second row
So how
minus
does he do
that
it?
equation. 0, 1, 2, and then I have a minus 3, and the
Did you flip
augmented
it?
part of it. 1
No.
minus, I'm replacing the
No.
first row with the first row minus the second row. So 1 minus 0 is 1. 1 minus 1 is 0. No, I don't want to make it.
So
1
he did
minus
flip
1
it.
is
Okay.
0. 1 minus 2 is minus 1. And then 3 minus minus 3. So that's equal to 3 plus 3.
I thought you were supposed to go in an L shape. 0, 0, 0, and then 0, 0, 0.
So that's equal to 6, right? 1 minus 0 is 1. 1 minus 1 is 0, negative 1. And then 3 minus the third row minus 2 times the second row. So we have 0 minus, well, 2 times 0. That's just going to be 0. 2 minus 2 times.
Okay, yeah. Okay. That makes more sense. I didn't see that. So the first row would stay the same. And the second row would stay the same. The third row would be 2 times the second row. So 2 times 0 minus 2 would just be... That still gives you... That's not a 0. Oh no, it's 0 times 0. Bruh. So 2 times 0 is 0. Minus 0 is still 0. Okay. And 2 times 1 is 2. Minus 2 is 0. And then 2 times 2 is 4. Wait, 2 times 2 is 4, minus 3, that's 1. And then 2 times 3 is 6. So that's negative 6. Negative 6 minus negative 5, so negative 6 plus 5, so that's negative 1. Okay. We can solve from here. We can go into row echelon form, which is, we gotta get a 0 up here. So 2 times, rather 1 times 1. So row 2 minus row 1. And 0 minus 1, no, row 1 minus row 2. So these will stay the same. 0, 1, 2, 0, 0, 1. Negative 1, negative 3. And then 1 minus 0 is just 1. 1 minus 1 is 0. And then 1 minus 2 is negative 1. And then what did I do? 3 minus negative 3. So that's 3 plus 3. That's 6. Okay. Now we need to get the negative 1 to 0. We get the 2 to 0 first. This will be 0, 0, 1, negative 1, 1, 0, negative 1, 6. And the second row would be the row 2, row 1, row 2 plus row 1 should do it. 0 plus 1 is just 1. Wait, no. Row 1 minus row 2. Nope. Let's do row 3. So row 1, row 2 minus 2 times row 3. Right? A 1 minus 2 times 0. It's just 1. Yeah, so row 2 minus 2 times row 3. So 0 minus 2 times 0 is just 0. 1 minus 2 times 0 is just 1. 2 minus 2 times 1. So 2 minus 2, that's 0. Negative 3 minus 1 times 0 is 1. Negative 3 plus 1. Negative 3 minus negative 1 times 0. That's 0. And 3 minus 0 is just negative 3. And the last one is 0, 0, 1, 0, 1, 0, 1, negative 3, row 1 minus row 3 minus row 1. 0 minus 1, nope, row 1 plus row 3. So row 1 plus row 3. So row 1, which is 1, plus 0 is just 1. And then 0 plus 0 is 0. Negative 1 plus 1 is 0. Can you please? Not funny. Row 1 you just completely messed up my whole train of thought. Thanks. Thank you, Deborah. What was I even doing? Row 1 minus row 3. Alright. Row 1 minus row 3. So 1 minus 0, 0, 0 minus 0, 0. And then negative 1 minus 1. Nope. So row 1 plus row 3. Negative 1 plus 1 is 0. Minus 6 plus 6 minus 1, that's 5. So the answer should be x is equal to 5, y is equal to negative 3, and z is equal to negative 1. 5, negative 3, and negative 1.
1. That's 2 times almost 0
5, negative
row
3, and
echelon
negative 1.
plus 0 y2 minus 1. That's that row right there.
Huh.
And then finally, we have 0.
5, negative 3, negative 1. How do you get rid of this negative 3? 0, 1, 2, negative 3. Oh, I didn't evaluate it, did I? What did I do here? Let's get the 2 to a 0. I did. Row 3. 2 row 3. Minus row 2. So 2 times 0 minus 0 is 0. 2 times 0 minus 1. Nope. So row 2 minus 2 row 3. Row 2 minus 2 row 3. Row 2 minus 2 row 3. 0 minus 2 times 0 is 0. 0 minus, so 1 minus 2 times 0 is 1. 2 minus 2 times 1, which is 2. 2 minus 2 would be 0. And negative 3 minus, that's what I remember. Negative 3 minus, plus 2 times 1, which is 2. So negative 3 plus 2 is negative 1. Alright. That should be negative 1. Please out of my chat, Amy. Negative 5, negative 1, negative 1. 5, negative 1, negative
plus
1.
0y minus our system of 3 right there. I just wrote it in this way just so you see it corresponding, but obviously I could have written them closer to their equal sign.
Alright, I got it. Thank you.
Figure it never hurts getting as much practice as possible solving systems of linear equations. So let's solve this. What I'm going to do is I'm going to solve it using an augmented matrix, and I'm going to put it in reduced row echelon form. So what's the augmented matrix for this system of equations? 3 unknowns with 3 equations. So it'll be, I'll just have to do the coefficients. So the coefficients of the x terms are just 1, 1, 1. Coefficients of the y terms are 1, 2, and 3. Coefficients of the z terms are 1, 3, and 4. 1, 3, and 4. And let me show that augmented. And then they equal 3, 0, 3, 0, and minus 2. Now I want to get this augmented matrix into reduced row echelon form. So the first thing, I have a 1 leading 1 here. That's a pivot entry. Let me make everything else in that column equal to a 0. So I'm not going to change my first row. So it'll just be a 1, a 1, a 1, and then my dividing line, and then I have a 3. Now, to make to 0 this out, let me just replace the second row with the first row minus the second row. So 1 minus 1 is 0. 1 minus 2 is 1 minus 2. Actually, a better thing to do, because I eventually want this to be 1 anyway. Let me replace this row with the second row minus the first row, instead of the first row minus the second row. I can do either way. So the second row minus the first row. So 1 minus 1 is 0. 2 minus 1 is 1. 3 minus 1 is 2. And then 0 minus 3 is minus 3. Now, I want to also 0 this out. So let me replace this guy with this equation minus that equation. So 1 minus 1 is 0. 3 minus 1 is 2. 4 minus 1 is
I'm just
3.
waiting for my x.
Minus 2 minus 3 is minus 5.
X. Let's do this.
Here are three linear equations of four unknowns, and like the first video where I talked about reduced row echelon form and solving systems of linear equations using augmented matrices, at least my gut feeling says, look, I have fewer equations than variables, so I probably won't be able to constrain this enough, or maybe I'll have an infinite number of solutions, but let's see if I'm right. So let's construct the augmented matrix
What's up,
for this
mathematician? Yeah, I
system
remember
of
you.
equations. So my coefficients on the
I think it was
x1
from like
terms are
maybe
1,
I haven't streamed a
1,
lot, so maybe
and
like two,
2.
three streams ago.
Coefficients on
Yeah.
the x2 are 2, 2, and 4. 2, 2, and
Ooh.
4. Coefficients on the x3 are 1, 2, and 0. 1, 2, and 0. There's, of course, no x3 term, so we can view it as a 0 coefficient. Coefficients on the x4, 1, minus 1, and 6. 1, minus 1, and 6. And then on the right-hand side of the equal sign, I have 8, 12, and 4. 8, 12, and 4. There's my augmented matrix. Now let's put this guy into reduced row echelon form. So the first thing I want to do is I want to zero out these two rows right here. So what can we do?
Struggling to fall
So
asleep.
I'm
I'm
going to
having
keep my first
insomnia.
row the same and
I go to
6.
bed at like 2
And then on
a.m.
the
every
right-hand
day,
side of the
so
equal
you're
sign, I
not
have 8,
alone.
12, and 4. 8, 12,
Maybe.
and 4. There's my augmented matrix. Now let's put
Go to
this
bed at like
guy
2,
into
1,
reduced
1:30.
row
I don't know how long you
echelon
stay up
form.
though.
So the first thing I want to do is I want to zero out these two rows right here. So what can we do? So I'm going to keep my first row the same for now. So it's 1, 2,
What do you mean
1,
you can't sleep? What do
1,
you do when
8.
you're not sleeping?
And that's
Did you
that
have
line
insomnia
essentially
anytime in your
represents my
life?
equal sign.
Insomnia? I mean, I've never got it diagnosed, but I just go to bed late sometimes. So I don't know if that's what insomnia is. It's like insomnia is like you can't sleep, right? I can sleep. I just choose not to go to sleep, essentially.
But let's see if I'm right. So let's construct the augmented matrix for this system of equations. I have here three linear equations of four unknowns, and like the first video where I talked about reduced row echelon form and solving systems of linear equations using augmented matrices, at least my gut feeling says, look, I have fewer equations than variables, so I probably won't be able to constrain this enough, or maybe I'll have an infinite number of solutions, but let's see if I'm right. So let's construct the augmented matrix for this system of equations. So my coefficients on the x1 terms are 1, 1, and 2. Coefficients on the x2 are 2, 2, and 4. 2, 2, and 4. Coefficients on the x3 are 1, 2, and 0. 1, 2, and 0. There's, of course, no x3 term, so we can view it as a 0 coefficient. Coefficients on the x4, 1, minus 1, and 6. 1, minus 1, and 6. And then on the right-hand side of the equal sign, I have 8, 12, and 4. 8, 12, and 4. There's my augmented matrix. Now let's put this.
How's my life been? I'm good, man. I've been chilling, just getting ready for the semester to start, honestly. I'm getting impatient. It's pretty much the same thing. Wake up, steady, work out. But yeah, I'm just waiting for my semester to start, honestly. And that is pretty much it. How you been? What's going on in your life? I'm trying to remember exactly who you are. If you're the one who told me. No. Yeah, that was you. Okay, yeah. In high school? Shanae. OMG, why, what's going on? Yeah, you're the one in high school who was asking me about SAT scores and stuff, yeah. Yep, yeah. I remember. This is why you can't tell Amy anything, Shanae. Don't ever tell Amy anything. When do you have to take the SAT? When is it?
Guy into reduced row echelon form. So the first thing I want to do is I want to zero out these two rows right here. So what can we do? So I'm going to keep my first row the same for now. So it's 1, 2, 1, 1, 8. And that line essentially represents my equal sign. And if let's see, what I can do is let me replace the second row with the second row minus the first row. So 1 minus 1 is 0. 2 minus 2 is 0. 2 minus 1 is 1. 1, negative 1 minus 1 is minus 2. And then 12 minus 8 is 4. There you go. That looks good so far. It looks like column or x2, which is represented by column 2, looks like it might be a free variable, but we're not 100% sure yet. Let's do all of our rows. So to get rid of this guy right here, let's replace our third equation with our third equation minus 2 times our first equation. So we get 2 minus 2 times 1 is 0. 4 minus 2 times 2, well, that's 0. 0 minus 2 times 1, that's minus 2. 6 minus 2 times 1, well, that's 4, right? 6 minus 2. And then 4 minus 2 times 8. Minus 2 times 8 is minus 16. 4 minus 16 is minus 12.
I'm trying to see what the point of this is, because we just did the exact same thing.
Now what can we do? Well,
Trying to
let's
show it
see if we
has
can get
no
rid of this
solution.
minus 2 term right there. 2. That's actually, so I had another completely
So if you got, hold on.
I just kind of mechanically
Can't go any further than that.
put this in reduced row echelon form. Actually, almost exactly like a computer. But let me put it back to my system of linear equations to see what our result is. So we get 1 times x1.
x1 plus 2x2.
So I get 1 times x1
plus 3x4
plus 2 times x2 plus 0 times x3 plus 3 times x4 is equal to 4. Obviously, I could ignore this term right there.
What do you use vectors for? Can you teach me dot product? Dot product is used to check. So if you take the dot product of two vectors, you're checking essentially how much one vector lies on another vector, if that makes sense. I'm trying to figure out how I can explain it in like easy terms. So if you take the dot product of two vectors, you're gonna get a scalar. And that scalar essentially, if it's 0, that means the vectors are perpendicular. Like none of them lie on any of them, if that makes sense. Their projections aren't like, hold on. Their projections aren't, essentially, vector A is not projecting on vector B. What's the use of vectors? It's used in everything really. Physics, engineering. That's why vector essentially has magnitude and direction. So if you have a force is you can think of a force in physics like a vector. It has how much of the force there is. So essentially how much force there is, and then you have the direction of the force, up, down, left, right. The force of gravity is a vector. It points downwards, and it has mass, right? How much gravity is pulling on you. That's an example in physics. And coding, it's used to make video games, for example. You want to know like collisions and stuff. If a player runs into an object, well, you can simply check that by getting the dot product of two vectors, the player's vector and the object's vector. And if their dot product is 0, then you know they're facing the same direction, essentially. Stuff like that. It's like I just started learning linear algebra, I want to say like a month ago, and honestly I've learned a good amount. Like it's one of the more interesting maths, I'll be honest. I didn't think it was at first, because I remember the first time I tried to take it, I was in college at Sam Houston. But yeah. Your dot product tells you how much two things are going in the same direction. There you go. That's the term I was looking for. It's about three-dimensional. It's about planes. Yeah. Or you can have two-dimensional vectors also. So, or n-dimensional vectors, yeah. Stuff like that. I didn't do anything with vectors until I was in college. Like the most math I took in high school was like, I think we took algebra and then we took geometry and trig. That's pretty much it. And pre-calculus. I took pre-calculus in high school.
I didn't even have to write it. Then, actually, I'm not going to write that. Then I get 0 times x1 plus 0 times x2 plus 1 times x3. So I could just write that. Well, I'll just write the 1. 1 times x3 minus 2 times x4 is equal to 4.
Yeah, you're welcome.
And then this last term,
I'm not really good at explaining stuff, so I probably confused you a little bit. But yeah, if you start studying linear algebra, you're gonna. I don't know if you already are, but it's gonna become clear essentially. And if you supplement it with like projects on the side, I use C++ to like build basic vector projects like I was doing today. You grasp it a lot easier.
I get 0 x1 plus 0 x2 plus 0 x3 plus 0 x4. Well, all of that's equal to 0, and I've got to write something on the left-hand side. So let me just write a 0, and that's got to be equal to minus 4. Well, this doesn't make any sense whatsoever. 0 equals minus 4. This is a nonsensical constraint. This is impossible. 0 can never equal minus 4. This is impossible. This is impossible, which means that it is essentially impossible to find an intersection of these three systems of equations, or a solution set that satisfies all of them. So when we looked at this initially at the beginning of the video, we said, oh, there's only 3 equations that have 4 unknowns. Maybe there's going to be an infinite set of solutions. But it turns out that these 3, I guess you can call them these 3 surfaces, don't intersect in R4, right? These are all 4-dimensional in R3. This is the case of play. If you have parallel line entries as columns, so it's just, one unique.
I don't think this is it's important, but as long as you know how to do Gaussian elimination, you should be fine. It's just doing too much. Maybe. All right. This is the important stuff. I'm tired. It's only 9:42.
In the last couple of videos, I already exposed you to the idea of a matrix, which is really just an array of numbers. And so usually a 2-dimensional array. Actually, it's always a 2-dimensional array for our purposes. So if I have an m by n matrix, m by n, the m is just the number of rows, and then the n is just the number of columns. So let me write out the m by n.
Is this matrix multiplication? Because I know how to do this.
Let's have the m by n matrix A. It's a capital, bold A. And it's equal to, I'll be as general as possible. First entry is I'll just call that lowercase a. It's in row 1, column 1. The next entry is row 1, column 2. And you go all the way to row 1, column n, right? You have n columns. And then when you go down, the next row will be row 2, column 1. And then you keep going all the way down to row m, column n. And then, of course, what this entry is going to be row 2. Let me write that a little smaller. Row 2, column 2. And you go all the way, and you're going to have row m, column n. And so if you think about it, you're going to have how many total entries here? You're going to have m entries this way, n that way. So you're going to have m times n total entries. And I think you're pretty familiar with this idea already of a matrix. You probably saw this in your Algebra 2 classes. So what we want to do now in this video is relate our notion of a matrix to everything we already know about vectors. Or maybe introduce some operations that allow matrix and vectors to interact with each other. And maybe the most natural one is multiplication, or taking the product. So what I'm going to do in this video is define. I'm going to define what it means when we take the product of our matrix A. Number of components has the same number of components.
The rows, the columns on matrix A has to match the rows on vectors X, on vector X, for it to be able to multiply. So if you have a 3 by 2 and a 2 by 2, you can multiply it. If you have a 3 by 2 and a 1 by 2, you can't, essentially.
As A has columns. So this is only valid for an X that looks like this. An X that looks like...
Yeah, area and integration, calculus, that's fun. Yep. That also ties into physics. There you go. A lot, actually. Taking, yeah. I have a whole book right here, actually. It has a bunch of those examples. And essentially ties in physics to calculus. I would recommend right here. It's pretty much calculus in physics. Or physics in calculus. So yeah, that's also fun. Integrating, taking area. You didn't do physics yet? Yeah. Or when you get there. That book is on Amazon. Great book. I still haven't gone through all of it, so.
This.
You just learned. Yeah.
X1,
Was that in like a pre-calc
X2.
class, or were you taking calculus? Because I didn't learn about that till I got to college, actually. Anything calculus, really. Yeah.
All the way down to xn. So let me be very clear this. This vector right here, it could be a different, I guess you could do it a different height than this vector. What matters is that the same number of a's you have in this direction, you have n a's here, then you have n components of this vector right here. And if you have that constraint, if the length of your vector, the number of components in vector, is equal to the number of columns in your matrix, then we define this product to be equal to, so that's my vector x. So this is a definition. There's nothing in nature that told us it had to be defined this way. It's just human beings or mathematicians decided that this is a useful convention to define the multiplication or the product of a matrix and a vector. So we're going to define A times our vector x. These are both bold, or this is a matrix, that's a vector. And the convention, if I didn't draw the little vector symbol, your textbooks will just bold out the x. So it'll be a lowercase x. Lowercase is vector, uppercase is matrix. Both of...
This is perfect right here. Khan Academy. Yeah. This is how I actually got started. Other than the fact I took linear algebra in college, but for half a semester. This what's it called? It has 3 sections right here. This teaches you all about like basic vectors. If you have access to Khan Academy. And then it just keeps going and keep going. The videos are super in depth, but it helps you like really understand what vectors are, not just like, okay, vector is an arrow, it has magnitude, it has direction, whatever. It like breaks it down, tells you what dot product actually means. Like everyone can take the dot product of 2 vectors, but not everyone knows exactly what it means, which is what you technically need to know. All right. So this is a great starting point. Like I said, it starts from pretty bare bones,
quantity
like
just by itself.
basic.
This is considered to be a. So let's say size is the same vector. It's how much we're moving.
15 minutes a day, 30 minutes a day. The videos are pretty short. They're not. He keeps them short, which is good. So you can always like do a couple, come back, and then do a couple again. Yeah, and if you know how to program, I've been working on this vector calculator. I was working on it earlier. Oh, this is the complicated version, but if we go on my GitHub. I made a simple vector calculator. There you go. Implementing vectors and taking dot products and stuff. I go to my like oldest commits right there, for example. No, that's messy. It just essentially takes vectors. Like the key is just to like implement it somehow so you can retain the information, not just okay, this is how you do it and then do it. If that makes sense.
Both of them are bold.
So I'd recommend Khan Academy on YouTube. Just vectors. It's pretty like it's linear algebra is like its own math, so it doesn't require you to know like calculus, for example. It doesn't require you to know, as long as you know basic algebra. For the most part, you're just multiplying, adding, subtracting. When it's the way you're doing it that's different. So yeah. YouTube Khan Academy. That's what I'd recommend.
But that tells you that you're not just dealing with regular numbers. So we're defining this to be equal to, let me write it out, fairly large. You're going to take each row, you're going to take each one, I'm going to show you that there's multiple ways to kind of visualize
you
this.
are welcome.
A11 times x1, let me write that down. So A11 times x1 plus A12, A12.
Right, vector multiplication is just rows times columns. So this entire row times this column. So A12 times x2, A13 times x3, A14 times x4, A1n times xn. That's all it is.
A11 times first, so the product of this matrix, this m by n matrix, and this n component vector will be a new vector. The first entry of which is essentially each of these entries times the corresponding entry here, and you add them all up. And as you can see, that's already looking fairly similar to a dot product. I'll discuss that in a second, but let me finish my definition before I start talking about what it means or what it might be related to. So that was that first row right there. It'll just look like that.
Second row, again, A21 times x1, A22 times x2.
We just multiply the second row, we'll have, but this time we're multiplying this row times A2n times xn. So we multiplied this entire row.
I take notes when I don't know it. Like I've already done this particular, like matrix multiplication. I watched the video on it on OpenCourseWare. That's this, Mr. Gilbert Strong. I watched a couple of videos on here already about essentially the first 3 videos on here. So I already know how to do matrix multiplication, but I take notes a bunch actually. Yeah. So I'm not taking notes because I already know how to do matrix multiplication.
Column, this term times that term plus this term plus this term, all the way down to this last term times that last, all the way down to plus this last term times that last term.
But the thing with Sal on Khan Academy, he has good points sometimes. So there'll be stuff he's gonna say something in here that I don't know. So that's why I turn the speed up essentially.
Until we get to the mth row, and then the mth row will be AM1. Oh, sorry, this is AM1, right? This is the mth row, first column. AM1
times x1. AM2 times x2
plus AM2 times x2, all the way taking the dot product of this row vector with this column vector. And we're essentially taking the dot, well, it has an entry for each row. What does vector B look like? How many entries is it going to have? Well, it has an entry for each row of this, right? We're taking each row and we're multiplying it. We're essentially taking the dot product of this row vector with this column vector. And I'll be a little bit more formal with the notation in a second, but I think you understand that this is a dot product. We're taking each corresponding, the first component times the first component, plus the second component times the second component, plus the third component times the third component, all the way to the nth component, plus the nth component times the nth component. So this is essentially the dot product of this row vector. Row vector is just it's just you're writing a row. We've been writing all of our vectors as columns, so we could call them column vectors. You're just writing them as rows, and we can be a little bit more specific with the notation in a second. But what's this going to look like? Well, we're doing this m times, so we're going to have m entries. You're going to have b1, b2, all the way to b.
Yeah, so if you take a vector, for example, a 3 by 2, and you multiply it by a 2 by 2, you're gonna get a 3 by 2 in return, essentially.
N. If you view these as all as matrices, you can kind of view it as you have a you have, and this will eventually work for the matrix math we're going to learn. This is an m by n matrix, and we're multiplying it by, how many rows does this guy have? He has n rows, right? He has n components, and he has one column. So
So you
m by
get
n times
m
n by
times
1,
1.
you essentially, you can kind of ignore these middle two terms, and they will result with
Yeah.
how many rows does this guy have? He has m rows and one column. So if you take out these middle two terms have to be equal to each other just for the multiplication to be defined, and then you're left with an m by 1 matrix. So this was all abstract. Let me actually apply it to some actual numbers. But it's important to actually set the definition. Set the definition. Now that we have the definition, we can apply it to some actual matrices and vectors. So let's say we have the...
It's crazy when you plot points in 3D, you get something like cubes. What do you mean, like X, Y, and Z? You get cubes. Like the plane is, it looks like a cube, yeah, because it's 3-dimensional. But were you here earlier in the stream? I don't know if you saw the program I made. We can actually plot 3D vectors, just normalized vectors. I can show it to you if you. I don't know if you were here earlier, or if you just scroll back in the stream. Honestly, it's in there.
Matrix. Let's say I want...
Yeah, I got you. He made a. Oh, it's a vector calculator. Like I said, I usually try to tie in stuff I'm learning into C++ or whatever. It's a vector calculator I've been working on for like the past, I guess, month or so. Slowly building on it, but so if we run it, it can do like basic vector, addition, subtraction, multiplications in C++, yeah, and can get you the dot product of a vector, a cross product. You learn about cross products, it's for 3D vectors. But when it comes to plotting the vector, if we want to plot the vector, for example, 1, 0, which is just the x-axis, and then 0, 1 is just the y-axis, right? You can actually plot the vector and you can see it in 2D, right? And that's the resultant vector. So that's what you get when you add the vector 1 and vector 2. But you can also plot in 3D, which I implemented today. So yeah, we can do 1, 0, 0, for example. Let's just plot, I don't know, the point 10, 20, 30, and then the point -10, -20, -30 in 3D, right? And it actually gives you a 3D plot of it. It doesn't look as cool, but I did that today, so yep. That's essentially what it does. And then obviously you can add vectors. You can add 2D vectors. For example, 1, 2, 3, 3, 2, 1. And you get the vector 4, 4, 4, right? Yeah. But if you plot 3, 2, 8, and 9, 14. And there's your vectors in 3D. Just like that. It's a little clunky. Yeah, there's z-axis, x-axis, y-axis, and then the blue one is the resultant vector. But yeah, that's what I was working on today. Fixing some of the code. Yep. If you just scroll back in the stream, actually, that's where I was working on it.
I want to multiply the matrix. -3,
Yep.
0,
Thank you.
3, 2. I'll do this one in yellow. 1, 7, -1, 9. And I want to multiply that by the vector. Now, how many components or rows does this vector have to have?
It has to
Well,
have
my matrix
4,
times vector
since it's a
product or
2 by
multiplication is only
4.
defined
It's
if
a
my
2
vector
by
has as
4,
many
so it has to
components
have a
as this
4 by
matrix
1.
has columns. So we have 1, 2, 3, 4 columns. So this guy's got to have 4 components for us to even be able to multiply them. Otherwise, it wouldn't be defined. So let me put 4 entries here. Let's say it's 2, -3, 4, and then -1. So what is this going to be equal to?
Let me try to do this. Well, not try. I should be able to do this and get the right answer. So -3, 0, 3, 2, 1, 7, -1, 9, multiplied by 2, -3, 4, -1, Alright, so that's row times column. So we take our -3 times 2 plus 0 plus 12 plus -2, and then 1 times 2, so that'll be 2 plus 7 times 3, so that's -21 plus, or rather plus, yeah, plus 4 times 1, that'll be -4, and then 9 times -1 would be -9. So this will equal the vector -3 times 2, that's -6. So -6 plus 12 is 6. So this is 4. And this is -21 minus 4, -25 minus 9. That'll be -34. Right? Is it -34? -25 minus 9. 25 minus 9 is -34 plus 2, -32. I think that's correct. Yeah. All right, so the vector should be 4, -32,
This is
if I did it
times
right.
1 times, this is 12, minus
Maybe? All right, hold on. So it should be, this is a 2 by 4. So we should get a 2 by 1
2
as a
minus 6.
resultant.
And like I said, you can
All
view
right,
it.
yeah, so that is correct. So 4,
And
-32.
let me be very clear right here. Well, everything we've been used to right now, we've been writing our vectors as column vectors. But you can view these, you can view each of these right here. You can view each of these guys right here as a row vector. But let me do even better. Let's say that vector, let me call vector A, A1. So let me define vector A1 is equal to -3, 0, 3, 2. And let me define vector A2 to be equal to, vector A2 is equal to 1, 7, minus 1, 9. So all I did is I wrote these guys, but I wrote them in our standard vector form. I wrote them as column vectors. So what we can define to turn these guys into row vectors is the transpose function. And transpose, you just turn the rows into columns and the columns into rows. So if this is A1, then A1 transpose will just be the row version of this. So it's -3, 0, 3, 2. And then A2 transpose would be equal to 1, 7, minus 1, and 9. And then this multiplication right here, we can rewrite it as, this matrix, we can rewrite it as...
Oh, SAT grammar? No. Anything grammar? No. That's honestly, I need to work on that, because like writing essays and stuff, no. No. I don't think I've ever gotten higher than a B in any English class whatsoever. That's what that is, right? Or is that the reading part? I don't know. I know there's 2 sections, right? It's been years. Yeah. But anything English, writing papers, punctuation, fixing sentences, no, I'm terrible.
We have vector A1 transpose for the first row. A1 transpose, that's a vector. These are vectors. Now, row vectors. And then this is A2 transpose.
My last English
A2
class of any
transpose,
kind was
which
in
is a superscript.
2021.
This vector can be written exactly like this, right? Because the first row is the second row. Times the vector times, let me just call this vector, and let me just call this vector x. That right there is vector x. So this is right here vector x. We can now rewrite the definition as this would be equal to what? This first row right here that we wrote out, right here, this was a1 dot x, right? A1 dot x. And you know all about the dot products. This was, the first row was a1.
So wait, you just transpose these two and then multiplied it by x. Dot x, why don't you just, I guess.
1 dot x. Right? It's -3 times 2 plus 0 times -3 plus 3 times 4, right? It's a1 dot x. And this is useful because we haven't, when I defined the dot product, I only defined it with column vectors like this. So now I'm dotting two column vectors. I haven't formally defined a row vector times a column vector. So now I can say, look, if this is just a standard column vector like we've been working with, I can write my matrix as each row is the transpose of a column vector, or it's a row vector. Then I can write this product as just the dot products of each of these transpose, or I guess you could say the inverse transpose, with this vector right here. And then obviously the second row is going to be a2 vector a2 dot x dot x. Right? The second row is a2 dot x is 1 times 2 plus 7 times minus 3 right there, minus 1 times 4 plus 9 times minus 1. So just like that. So this is one way to view it. It's kind of matrix times the vector is just like the transpose of its rows dotted with the vector you're multiplying it by. This is one way to perceive matrix multiplication. Now the other way to perceive it, let me do it this way. So maybe I'll do it with a different example. Those numbers are getting a little bit tiresome. Let's say I have the matrix A, nice bold, is equal to, oh, I don't know, let me say it's 3, 1, 0, 3, 2, 4, 7, 0, minus 1, 2, 3, and 4. And I need to multiply this. I have to multiply this times a 4-component vector. So let me call vector x is equal to, I don't know, it's equal to 5. Actually, let me keep it general. Let's say it's equal to x1, x2, x3, and x4. Now, instead of viewing these as row vectors, we could view A as a set of column vectors, right? We could call this thing right here, we could call that vector 1. We call this thing right here vector 2. We call this thing right here vector 3. And we call this thing right here vector 4. Then we could rewrite our matrix A as being equal to just a bunch of column vectors. So we could rewrite it as vector 1, vector 2, vector 3 is vector 1, and vector 4. That's vector 4 right there. So how can the matrix multiplication be interpreted in this context? Well, what did we do? We multiplied. When we multiply these guys, we always do, all of the elements in here always get multiplied by x1, right? It's 3, let me start some of the multiplication here, just from our definition. So if I multiply a times x, I'll start it off. Maybe I won't do the whole thing. I just want you to see the pattern. It's 3 times x1 plus 1 times x2 plus 0 times x3 plus 3 times x4. That's the first entry. And then you have 2 times x1 plus 4 times x2. All the way, and then you finally have minus 1 times x1 plus 2 times x2. You get the idea. But what's happening here? This guy, this first vector, is always being multiplied by the scalar x1. In fact, you can view this part of the entries right here, right? We're just multiplying this guy times the scalar of x1 in every case, right? You have 3, 2, minus 1, 3, 2, minus 1. We're multiplying by the scalar of x1, and then we're adding that to this guy times the scalar x2, right? And we're multiplying, and then we're adding that to this guy times the scalar x3. So we can rewrite a times x, as being equal to the scalar x1 times the vector v1 plus the
Plus
scalar x2,
x2,
right? This is
v2,
the scalar x1 times the vector v1 plus the scalar x2 times the vector v2. I want to do that in yellow, times the vector
row
v2
times column.
plus x3
It's
times the
annoying because
vector
they teach the same
v3
thing in like 11
plus the
different
scalar
ways, and
x4
that's
times the
what
vector
confuses you.
v4. And obviously, if we
If they would just teach, again, all this has just been row times column. But I've heard about it in like 5 different ways now. Take the first row, 3103, times the column, 3 times x1, 1 times x2, and then go do it again for this row and this row. That's it.
had n terms here, we'd have to have n vectors here, and we could just take this, make this more general to n. But what's interesting here is now the product ax, it can be interpreted as a linear combination, right? These are just arbitrary numbers depending on what our vector x is. So depending on our vector x, we're taking a linear combination of the column vectors.
Do you know the math behind dot product? I know dot product of -1 means that two vectors are going in opposite directions. What do you mean the math? You mean how you find a dot product? Do you mean how do you find a dot product, or like we make a triangle? Yeah. I wish I had like a table camera, but I don't. I can show you what I mean on paper. I can write it out, but Do you mean like how you find the dot product? Is that what you're asking? Because it's just if you have two vectors to take the dot product, and so you have vector A, and is there a scratch pad here somewhere? No. Damn. See, if I was on my iPad, I can just write. I don't even know how you write on the screen on a computer. The math behind it. Well, another way to think of the dot product, it's the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle in between. But I feel like that's even more complicated than just taking the dot product, essentially. Um, let me see. Let's see where. He has a cut. He has a like. He explained the dot product really well. Let me see the video. Yeah, let me go to this video right here. Are you trying to? You're trying to see the proof of the dot product? That's what maybe what you're saying. No, that's just talking about properties. Uh,
We've already made just going to be a scalar right there. Let me do it. I've been measuring things since I was a kid. Why do I have to wait? If I were to draw my vector, it makes no sense, but we can still apply this notion of length and cool.
this isn't what I'm looking for. Whiteboard. You said whiteboard. I don't want to sign up either. I gotta sign up. I don't want to sign up to anything. I just want to write. All right, there you go. So what I was saying is, how does -1 mean they're going in opposite directions? All right, so I think I know how it's done. I could be wrong though, so I'm gonna try to explain it. So the dot product of two vectors, right? This is vector A, and then call this vector B. I know it has to do with Pythagorean's theorem, right? So if we take the dot product of, essentially that's this angle, right? Hold on. A dot B is equal to the magnitude times cosine theta. And if you remember, cosine of an angle is SOHCAHTOA, right? Ka, adjacent over your hypotenuse. The cosine of an angle is your adjacent over your hypotenuse. So we're given a vector. Let's say our angle is right here. Adjacent angle. So the adjacent would be B, rather. I'm just trying to draw in my head and explain it to myself before I explain it to you. Hold on. Me trying to prove dot product, even though that's Khan Academy. And 0, 1, 2, sine 0, 0, sine 1. 2 divided by 2. 1 divided by 2. Two over 2 is 1. How does the unit circle go again? It's 0, 30, 45, 60, 90? Right? This is 3 over 2. 60, 90, yeah. And this is 4 divided by 2 is just 2. So it's so all right, so the dot product, right? The dot product is taking a linear combination of, well, if you think of it that way. So if you have the vector 2, 1, right? Let's say 2, 1 is A dot, I don't know, 1, 2, for example. I don't know if this will even work. You do essentially 2 times 1 plus, right? So it'd be 2 times 1 plus 1 times 2. And that would be your dot product, which would be 4. So in vectors, I don't know if you've ever dealt with vectors, but if you want to add a vector, you essentially go tip to tail, right? So if you want to add this vector A with this vector B, we go tip to tail. So we put this tail at this tip right here. And the resultant vector would sort of form a triangle. Does that make sense? Does that part make sense? So if you want to add how you add a vector, do you know that? So if you have two vectors, right? Vector A, and let's say vector B points this way. If you want to add vector A to vector B, you simply just have to put vector B at the tip of vector A, like so. And then this would be your resultant vector, right? Your resultant vector would go this way. Yeah, I'm going to. It would go this way. All right, so that's your resultant vector. Well, as you can see, it always forms a triangle, right? Your resultant vector is always, no matter what two vectors you add, it's going to form a triangle. So this will be your first vector, this will be your second vector, and that's will be your third vector. Some form is going to be on this line, right? As a resultant. That's pretty much, so you're taking a dot product, you're essentially combining two vectors and getting a scalar, which is the magnitude. And that scalar is essentially the magnitude of this vector right here, right? And that's your hypotenuse, essentially. So giving one vector, A, and you have your hypotenuse, which is the magnitude of B. Cosine is your adjacent over hypotenuse. And remember, cosine of 0, right? If the dot product is 0, so you're essentially just taking cosine of 0. Rather 90 degrees, sorry. If the cosine of 90 degrees is 0, so if the dot product is 0, that means it's perpendicular, if that makes sense. That hold on. Let's watch the video, man. Cause I'm trying to explain it, but he did it. There's one of these videos on here. He did a great job of explaining it, and it clicked. It's not this one. No. Here.
Perpendicular when a dot b is equal to 0. A and you think of it that word. And you're saying, Sal, what does that do for me? I'll do that in magenta. Is equal to the adjacent side. So this...
I don't know how to explain it. Like, yeah, it's adjacent divided by your... Yeah, it's this video.
Video in the physics playlist where I compare the dot product to the cross product. And I'm doing it in length. Cosine of theta is equal to adjacent over hypotenuse. So if I create a right triangle here, and let me introduce some new colors just to ease the monotony. If I drop a right triangle right here, and I create a right triangle right there, and this is theta, then what is the cosine of theta? It's equal to this.
Yeah, cosine of theta would be adjacent, which is your b, over hypotenuse, which is your a.
It's equal to this, the adjacent side. It's equal to this little magenta thing, not all of b, just this part that goes up to my right angle. That's my adjacent. Now I want to do a little bit bigger. It's equal to the adjacent side over the hypotenuse, right? So let me write this down. So cosine of theta is equal to this little adjacent side. I'm just going to write it like that. Is equal to...
I told you my explanations are going to confuse you even more if I try to...
Side over the hypotenuse. But what is the hypotenuse? It is the length of vector A. It's this. That's my hypotenuse.
Magnitude.
My hypotenuse is the length of vector A. And so if I multiply both sides by the length of vector A, I get the length of vector A times the cosine of theta is equal to the adjacent side. I'll do that in magenta. Is equal to the adjacent side. So this expression right here, which was just A dot B, can be rewritten as, I just told you that the length of vector A times cosine of theta is equal to this little magenta adjacent side. So this is equal to the adjacent side. So you can view A dot B as being equal to the length of vector B, that length, times that adjacent side. And you're saying, Sal, what does that do for me? Well, what it tells you is you're multiplying essentially the length of vector B times the amount of vector A that's going in the same direction as vector B, right? You can kind of view this as the shadow of vector A, and I'll talk about projections in the future, and I'll more formally define them, but if the word projection helps you, just think of it that word. If you have a light that shines down from above, this adjacent side is kind of like the shadow of A onto vector B. And you can imagine if these two vectors, if our two vectors looked more like, if they looked more like this, if they were really going in the same direction, let's say that's vector A and that's vector B, then the adjacent side that I care about is they're going to have a lot more in common. The part of A that is going in the same direction of B will be a lot larger. So this will have a larger dot product. Because the dot product is essentially saying how much of those vectors are going in the same direction, but it's just a number. So it'll just be this adjacent side times the length of B. And what if I had vectors that are pretty perpendicular to each other? So what if I had two vectors that were like this? What if my vector A looked like that?
Yeah.
Vector A looked like that, and my vector B looked like that. Well, now the adjacent, the way I define it here, if I had to make a right triangle like that, the adjacent side is very small. So your dot product, even though A is still a reasonably large vector, is now much smaller because A and B have very little commonality in the same direction. And you could do it the other way. You could draw you could draw this down like that, and you could do the adjacent the other way. But it doesn't matter because these A's and B's are arbitrary. So the takeaway is the fact that A dot B is equal to the lengths of each of those times the cosine of theta. To me, it says that the dot product. So the dot product tells me how much are my vectors moving together, or the product of the part of the vectors that are moving together. Product of the lengths of the vectors that are moving together or in the same direction. Same direction, right? You could view this adjacent...
Yeah, I'm a terrible teacher. I will remember not to ever teach. But yeah, like I was saying, that's adjacent over essentially hypotenuse, right? But just the adjacent side that's not, so not the whole, just the adjacent side that's reflected. For the most part, it's trigonometry. That's how the dot product is derived, essentially. And the cross product's for 3D vectors, but... Yeah, you're welcome, man. The thing about it is you have to do it a good amount of times. Like even I still feel like I haven't done it a good amount of times. You have to do it a good amount of times to really. That's the thing with linear algebra. I feel like it's a lot of repetition. So
1, 2, and then I have a bunch of zeros over here. And then this has to equal 0. Remember, if this was a bunch of zeros equaling some variable, then I would have no solution.
we're done here.
Column vectors of A. So this is a linear combination.
Yeah, I'm about to go to bed too in a
Combination
little. Take care, man. I'll see you.
of column vectors of A. So this is really interesting. I'm sure you've been exposed to matrix multiplication in the past, but I really want you to kind of to absorb these two ways of interpreting it, because they'll be important when we talk about column spaces and things like that in the future, is that you can interpret matrix multiplication. And actually, there's other ways you can actually interpret it as a transformation of this vector x, but I won't cover that in this video just for brevity. But you can interpret it as a weighted combination or linear combination of the column vectors of A, where the matrix x dictates what the weights on each of the columns are, or you can interpret it as essentially the dot product of the row vectors, or you can define the row vectors as the transpose of column vectors, the dot product of those column vectors, each of the corresponding column vectors, with your matrix x. So these are both completely valid interpretations, and hopefully at least this video at least gives you a working knowledge of what matrix multiplication is, and even better, gives you a little bit deeper sense of all of the different ways that it can be interpreted.
So column vectors dot each component. So this times that, this dot that, rather. Or you said row vectors times column. Okay.
Are, or you can interpret it as essentially the dot product of the row vectors. Or let's review this is all a review. That if V members, and you'll get that, and it's an G are a member of, satisfy this equation. So what is A? So
I'm gonna go to sleep. Tired. Which of two things going in the same direction? Equal to 0.